So hello everyone, welcome back to another particular lecture series of our Reagent Chemistry course. So in our previous lecture, we are talking about the different nucleophilic epoxydating agents. So now in this particular class, we are talking about the dihydroxylation of double bond. So in this particular class, we are mainly focused on the osmium tetroxide and KMnO4 based dihydroxylation. So first of all, the dihydroxylation of a double bond that refers to the addition of two hydroxyl group across an alkene, converting it into 1,2-diol. So basically, in the previous segment, we are talking about that this react with the epoxidizing agent to generate a epoxide. Now here in this particular segment, we talk about that react with the alkene with different substrate to generate this 1,2-diol system. So basically, here the stereochemistry is not mentioned, but because sometimes there is a syn dihydroxylation takes place. Also, we are do the anti-dihydroxylation also. So for the syn dihydroxylation or the cis dihydroxylation, osmium tetroxide and KMnO4, this is a potassium permanganate has been used, which add both OH group on the same phase to the double bond. And for the anti-dihydroxylation, basically the normal method is to the epoxide generation, that initially epoxide has been generated and then epoxide has been treated with the acidic hydrolysis, that is the H plus H2O to generate the trans diol, we can say. Also, there is a name reaction also there in the pre-first method. From there also we can do the trans dihydroxylation in the double bonds. So we'll discuss in the next class, but in this particular class we are actually focused on the syn dihydroxylation using OsO4 and KMnO4. So let us talk about the osmium tetroxide first. Syn dihydroxylation via osmium tetroxide. So this is the osmium tetroxide, and osmium tetroxide is a toxic reagent, very toxic, and it always gives cis 1,2-diol. And the oxidation state of OS here, this is the 8, and this is the structure of osmium tetroxide, and the reaction is proceeded by a concerted mechanism, sometimes 3 plus 2, 2 plus 1 and 4 plus 2 reaction, out of which 3 plus 2 are most common. However, in certain cases, on the certain substrate, this 2 plus 1 and 4 plus 2 is also observed. So this is the starting material. It's actually react with the OsO4 to make a osmic ester that we will discuss in the mechanistic pathway. And the KSSO3 is used to break this particular bond to generate this product. And the trans diol is never formed. So this is never formed. Only this particular product is formed. And during reaction, this osmium oxidation number change from +8 to +6. That means that OS is getting reduced and this particular double bond getting oxidized. And this particular reaction is stereospecific in nature. So now let us talk about the mechanistic pathway of that particular reaction. So mechanism. The mechanism goes via concerted mechanism. So initially what happened that this particular OsO4 react with this particular double bond via 3 plus 2 cycloaddition to form this osmate esters. And this particular osmate ester is stable and isolable. Okay. So now this is KHSO3 has been used to cleave this particular OSO bond, and then after hydrolysis and the proton taken from the solvent to get, this is our product. There is the cis diol and this is the byproduct. This is the OS6, OSO3, where the oxidation state of osmium is +6. Here is also written that oxidation number of OS changed to +8 to +6, and a reagent such as the potassium bisulfate or sometimes sodium bisulfate is commonly used to break the OSO bond and liberate the diols. So the role of this potassium bisulfate and sodium bisulfate is to break this particular OSO bonds. I hope it is clear to you. Now let us talk about the regioselectivity. First, that the reaction rate generally increase with the increasing substitution of the alkene. That means the similar kind of trend we have observed in the case of MCPBA reaction, where the alkene at the most substituted, there is a more electron density present in that particular double bond, will undergo more reaction. So here it is written that tetra substituted are the fastest, where the mono substituted is the slowest in the particular reaction. So this is the product. Similarly, in the OsO4 actually attacks from the above side to generate this particular product, and this is because to eliminate the steric repulsion, as similar of the we had discussed in the MCPBA part also. However, the same that the reaction rate generally decrease if the alkane is attached to electron withdrawing groups. Like here in this between these two particular double bond, this double bond are electron deficient and this particular are electron rich. This is electron deficient because of this particular two electron withdrawing group, and that's why OsO4 on the osmium tetroxide are actually attack here, and here these are all OS, small s. Okay, so this is the final product. And now let us talk about the stereoselectivity. So this is also a stereospecific in nature, where the cis, these two are the diastereomers, or the cis-pen twin, and the trans-pen twin, these two are diastereomer in nature, cis-trans. And after treatment with OsO4, these both are starting material, these two are final products, are also diastereomer. That means these are the stereospecific reaction, just similar like the MCPBA based reaction. So between MCPBA and OsO4 based reaction, both are very much similar, but they are shown different products. Now let us talk about the other selectivity, like in presence of adjacent group. So usually dihydroxylation that is occurs from the less hindered side, where no hydrogen bonding influence in presence of just OsO4. However, if in presence of tameda is called the tetramethyl ethylene diamine. So the structure of tameda is this, and if the tameda is present in the reaction medium, then directed hydrogen bonding has been prominent, and then directed dihydroxylation observed. Same example here, the same reaction condition, but tameda is used here. Then you can say the stereochemistry is same as the directing group stereochemistry because of the hydrogen bonding. But usually in the case of normal osmium tetroxide, it will not show any kind of hydrogen bonding. Now let's talk about the catalytic OsO4 reaction. Like OsO4 is too costly. That's why actually in practical cases, that OsO4 is not used in the stoichiometric fashion, it is used in the catalytic fashion. And in presence of a terminal oxidant, the terminal oxidant is the NMO, that is the N-methyl morpholine N oxide. What does it do actually? So after reaction, osmium tetroxide, it is initially the osmium is the +8, so it will getting reduced to +6. So then what happened, that in presence of NMO, this actually again do the oxidation of this particular OsO3 to OsO4, and then this particular OsO4 then again go via reaction pathway, and the N-methyl morpholine N oxide now become N-methyl morpholine only. So this is getting reduced, and this particular OsO3 getting oxidized, and that's why OsO4 now can be used in the catalytic fashion, where the NMO is used in the stoichiometric fashion. Here it is written that NMO oxidize OS6 to OS8, and it itself gets reduced to N-methyl morpholine. However, in absence of NMO, H2O2 can also be used as a terminal oxidant, but NMO is widely used as a terminal oxidant. Now KMnO4. KMnO4 is also capable to do cis dihydroxylation, where a treatment of alkaline with cold alkaline KMnO4 will give vicinal diol. This is a cis diol. Cis diol. So this is also follow the same mechanism just like osmium tetroxide. Like the 3+2 cycloaddition is there to form this manganate ester formation, and then in presence of base, it will actually show a cis dihydroxylation. But if the base is not present, then it will show oxidative cleavage between something like this, and this particular bond has been break and to form this two particular diol, two particular aldehyde, and this is the side product, and that's actually decrease the yield of this particular cis diol, and that's why in the case of cis diol formation, osmium tetroxide is mostly used to do cis dihydroxylation over KMnO4. So with this, we have to end this particular class. I hope this particular class, you will understand that particular class. So in the next class, we are talking about the some two name reaction that is actually useful for synthesizing alkene to 1,2-diol. That is the Woodward and Prevost reaction. So thank you for listening.